Life.
Hello, everyone. Good morning, good afternoon, good evening, wherever you are. It's our pleasure, together with Sebastian Geiger, myself, to host you again. This is our 111th Geoscience and Geoenergy webinar today, 16th of February 2023. It's our pleasure and honor to host our dear friend and colleague, Florian Wellmann, today as our speaker. Excuse me. Florian studied geology with a focus on applied geosciences and geophysics at Tübingen University in Germany. After a detour for an overwintering campaign in Antarctica, he started working on geothermal topics. In his work, he focuses on the integration of geological, geophysical, and geothermal simulations for optimal data integration and the quantification of uncertainties. He obtained his PhD degree at the University of Western Australia. Nice place to be as a geothermal expert, my friend. So
Yeah.
you had good
Yeah.
time. I can say. And in 2014, joined RWTH Aachen University, where he is now the head of the Institute of Computational Geosciences, Geothermics, and Reservoir Geophysics. Since mid 2022, just last year, less than a year ago, he's also affiliated with Fraunhofer IEG and leads the Competence Center on Exploration and Reservoir Simulation for geothermal projects. It's our honor and pleasure, Florian, to host you this week with us. And you have been in the list of invitees for a long time, so we finally could catch you for this talk, despite your busy schedule. It's start of also new academic quarter here in Delft as well. I don't know how Aachen folks are catching up with all these kind of teaching things. So we are all
Yeah.
very much looking forward to your talk. And after your talk, we will have questions and discussions. Sebastian will do that as always. And folks will text their questions in the chat box, and then Sebastian will engage into a debate or discussion with you. So to summarize and make sure the learning points are transferred. Um, you have about 35 minutes like everybody, but you are a good friend of us. 36 minutes would be fine. So somehow manage. We don't invoice more than €1,000 per minute extra. So that's all. So without any further ado, please take the stage. We are very much looking forward to hearing your lecture, especially as you look like you're embedded into the geology. So we are very much excited to see what is going on now.
Yes, thanks a lot, Hadi. Thanks a lot, Sebastian Hadi, for inviting me and everyone for joining and watching and the chance to present a bit of our work here. I've been following the webinar for many sessions, so it's really a pleasure to be here. And as Hadi said, somewhere in geology, but actually, I mean, we talked today about mostly things that are a bit below the surface, and I'm really happy that I have the chance here to talk a little bit about the recent work that we've been doing on probabilistic geomodeling, and hopefully a bit on the link to geothermal simulations, because I know that this is, of course, the topic of this entire webinar series, and I hope I can raise your interest also in these methods that have been developed in combining these aspects. So it's an afternoon session, and in Germany today, actually, it's also the beginning of Carnival. So in case some people are looking here as well, watching, I thought I'd set this a bit up as a drama to keep you all engaged. Like a bit of a sense of a Greek drama, where the first we're entering now the first stage, basically, where we have to set up the scene about the talk and the topic and the teaching content. So we start with the motivation, and as you do these days, I asked ChatGPT to tell me how to set up a presentation using a dialogue session in a sense to present the topic here. Let's see how I can live up to the suggestions of ChatGPT. Motivation. As I said, this is mostly the work is on this link between geological modeling and process simulations. But I would like to highlight a bit the general context and the idea of where all of these aspects come from, in a sense. I'm sure you have seen this this figure before, maybe not everyone, but many of you. This is from a report already dating back 10 years, but it's a concept basically showing how project risk over here on the left axis, on the upper axis, changes with exploration phases. This is for a geothermal project. And we have on this dashed line here, we have the cost, cumulative cost. And there's a lot to debate about this, this graph, but I think important points to realize. I think this is what we see here. At the beginning, we remain at a very high risk in a project in this pre-survey exploration phase. And this remains very high until we get to the first drilling. And that's something which we see a lot in geothermal projects, that there's, of course, this very high upfront investment and cost basically required to reduce the risk significantly. So the motivation basically for this work I'm showing is the question, how can we actually reduce the risk before we get to this point of drilling and before we have to make these huge investments? And in the end, to me, this comes down to the question if we can somehow at least quantify the uncertainties in our prediction about subsurface properties and expected gain from a geothermal system prior to this first drilling maybe, and to perform a better risk assessment in a sense. So before we look into this, just a very schematic workflow on this, say, typical geothermal processing. But quite commonly we start on some sense with the integration of all geological data that we have or geophysical data. So this can be typically, maybe you already have some seismic information, maybe you have some boreholes in the vicinity, potentially information from shallower regions. And we implement all of this information into what we typically consider as a geological model or a reservoir model, where we highlight the position of relevant geological and geothermal reservoirs basically in 3D. This is then taken forward to mesh generation of some sort that we need in order to go to the next step that we actually want to do, which is the process simulation, where we then take, let's say, our reservoir geometries and the rock physics properties, the properties inside a reservoir, and we perform dynamic simulations, for example, of a doublet well, to see how much we can extract, how much heat we can extract over a sustainable lifetime of a reservoir, and how we potentially should place maybe the wells. In the end, we get to a stage of visualization and further analysis. And I'm putting this here because in the end, this is something which is where quite often we do this in a 3D view, let's say. But commonly as well, we need to take this information from our simulation, the results, and either show them to stakeholders or maybe other people who continue working with this data. Or if we think back about this idea of risk, we want to take these results somehow and analyze those results. And that's a little bit something that I would like to talk about at the end, if I stay within the 36 minutes. Okay, so the big question is now we have this workflow, and that's commonly used in one form or maybe a bit of another. Depends on which methods maybe you specifically use and which scale you're looking at. But the big question is, can we use this workflow actually to estimate uncertainties, for example, in the predictions of our process simulations based on uncertainties in our prior geological model? And this is an aspect that if we look at it, of course, what becomes very quickly clear is that we want to use this workflow for quantification of uncertainties. We require an automation in this workflow. Why? I mean, we can go ahead and say, you know, we take our geological model and maybe we generate one or multiple scenarios to look at the effects of changing maybe the thickness of geothermal reservoirs or the dip of a fault and so on. And we may be able to generate then multiple realizations in this process. But if we really want to understand uncertainties and the effect of uncertainties, it needs to be automated because, as maybe you know, also these steps, especially from geological modeling to mesh generation, can take a significant amount of work, actually, of manual work. Okay. Today, though, I would like to start focusing on this first aspect, so the aspect of geological modeling itself. Because this is the first step that we need to automate when we want to consider uncertainties in this workflow. And this is where these ideas of probabilistic geomodeling that I'd like to talk about come into play. Also on this level, there is quite a hierarchy of modeling workflows that I would like to mention here, because I'm sure that some of you look at maybe other aspects than the one I'm talking about in geological modeling. And this is all important. All of these things have to come together. So if you look at the hierarchy, typically on the geological modeling scale, we start with what we can call a framework model, where we look at interfaces, main interfaces between geological units. Then we build stratigraphic models, and we fill those models maybe with property fields, for example, using multi-point geostatistics, or more and more now today machine learning methods. And inside each domain, we may perform property simulations using, for example, geostatistical methods. This is well used in different fields. What we do today is we will focus actually on this first part, which we can consider as mostly the geological modeling. And yeah, this here. Okay, so when we do these modeling methods now, again, one more maybe philosophical step or conceptual step on thinking what we actually do. If we look at a rock face this is here somewhere in the Pyrenees, and we see, you walk through the mountains, you look at the rocks, you see a really, really high level of complexity. You look at these big rock structures, we can see some differences between maybe these more gray areas up here. Down there, it's a bit more greenish. So we can directly see there's something happening. But of course, if we go closer and you look carefully, at a rock outcrop, you see a lot of variability inside. And if you even take a sample of a rock, you can see variability on all scales. In geological modeling concepts, so we go to multiple scales, yes. The point is that what we do in geological modeling concepts, we simplify all of this complexity into interfaces between areas with major differences in rock types, depicted here with these interface line here, and use this basically to substitute all of this complexity into a simplified version. Now, how do we do that? I mean, in reality, we cannot see the rock outcropping so nicely always. So because we are looking, under our feet into the subsurface. So what do we do? Well, we have to also combine a lot of information. Typically, we have maybe borehole data shown here, but always, be aware that this is just a very, very small singular point in potentially a large domain. So we fill the space in between with all kinds of geophysical methods, for example, seismic methods or other types of geophysical measurements, ERT, and so on. In the end, we reconstruct then this complexity basically in the form of what we call boundary representation. So we see here these interfaces that I've shown above in this picture in discrete interfaces, which basically delimit these areas with major differences in rock types. Now, this is all nice, and as I said, used a lot in different settings. The problem is, though, that all of this is not perfectly known. And there are several studies on, well, the subsurface is, let's say, our view into the subsurface is limited, as I said, to these, let's say, direct observations in boreholes and these geophysical measurements. And of course, we all know, you create a model, someone else creates a model, they will look different. This is something which is now in recent years been investigated quite a bit in different studies. Claire Bond, for example, has done a lot of work on these topics. And here's a nice example I would like to share with you. This is what they did here. The authors, they created an artificial section, basically, of we see here nice thrust sheets in between for the thrusting. And they extracted information now from this artificial model, basically along these boreholes. So extracted basically information along this 2D profile, gave this to interpreters and asked them to create models. And as you can imagine, we have now here examples of these models that were returned. And we can see that we have some parts, all of these red lines now depict basically these interfaces. We see in some regions, they agree quite well, all the experts, but then we have some other regions where there's a lot of deviation, a lot of variability in the interpretations. And this is, I would say, even a data set with a lot of information, because we see that we have all of these wells close to each other. And over here, where we see that the distance is getting wider, we see already very high uncertainties. So in this case, these were like 19 geologists with partly a lot of information, experience, so quite known to this task in a sense. And still, we see that we have significant uncertainties in these interpretations. And I would say that in reality, we quite often have a lot of less information, a lot less data than these nice boreholes here. We have to deal, especially in geothermics, quite often in the first stages with legacy data, which may be from 60s or 70s. And this is already quite highly complex setting, but when we now, of course, go from 2D to 3D, we can see that there are additional challenges, of course, coming up. So tricky. And the problem is, of course, now in our ChatGPT setup here, the question would be, we cannot always get 100 geologists for multiple models to represent this uncertainty in a sense. What can we do? And the logical approach, in a sense, from a practical purpose, would be to say, well, maybe we can find somehow a way to replicate all of these different interpretations by an automatic method, so by a stochastic simulation approach, for example. Okay, in order to do that, we first need to have a method that allows us to generate these models automatically, so geological models automatically from input data. And this is not so much part of this talk, but I would like to mention that in recent years now, there have been quite some approaches developed to enable this geological modeling automatically. And many of those are based on so-called implicit surface representations. We use here one which has been actually developed, the theory already by Lajonie et al. In 1997. The nice idea is that it's basically representing these interfaces in space as isosurfaces in a 3D scalar field. And without going into too much details here, actually, I skipped this directly. This allows us actually to generate fairly complex models, as we can see also here with faults, and we have like a nice basin structure with some faults in between. And you can see in the background this video playing. We change actually a point. This is a live screencast, and we see that changing a point directly, the structures in this model change, because we can use a very low dimensional parametrization of this full 3D model, and we get an automatic update basically. This is implemented in one of our open source packages, GemPy, which allows you then basically to generate these models automatically. Okay, so as we have this method now, we can then use this method in a stochastic simulation workflow. And the point is now, oh, wait, sorry, where do I have this? Okay, this is nice so far, but now we get to the second stage basically of our drama. And this is that we have now a nice theory. We have a problem identified. We have potentially a method to solve this problem. But now theory meets reality. In the context of a Greek drama, we get to the stage of confrontation. Let's see what this looks like. Well, we can say, okay, we have an automatic method to generate models. So what we can do theoretically is to say that we now take our geological data, our input data points for our geological model. I'm showing up here in these boxes, boundary points. So this could be picks from maybe seismic or identified interfaces in boreholes. And we can even include things like orientations, so maybe something which we can also identify from seismic data or from knowledge. And we can use this to create an initial 3D model. But now we don't stop there, but we actually assign distributions to all of these input points. So instead of saying that we have a single best fitting point information, we assign uncertainty to this information. And the question is now, how would we do that? Especially for a borehole, we can say, well, we know quite precisely what we have there, and I would agree. But a lot of information that goes into this model is coming from maybe only some vague expectations in a sense, or interpretations from seismic, where if you talk to the geologists creating these models, they will also happily tell you, okay, over here I'm quite certain, and over there actually I don't know that much. So this is information that we can then transform into distributions, ideally, and use to generate now, instead of one input data set, we now randomly choose parameters from these distributions. So we draw samples from these distributions for input data points, and we generate multiple realizations out of these different input data sets for our geological model. So what could this look like? I have an example here, basically, where we see that we have these red lines, green and purple, Now, these would represent, so each single line is the representation of one model result in a sense. And these multiple lines represent multiple draws from this stochastic distribution. And we can see, we have this, what we sometimes call spaghetti plots. We have these spaghetti plots here, which somehow they do resemble what we've seen up here, right? This was the example from Claire Bond and co-workers. We also see these multiple interpretations. So the big question is now, of course, is this actually comparable? Do we get something with the automatic method that we use here that we can actually compare to the variability that you would get if multiple people would interpret this data set? Okay, so this is, I think, for all who have ever been doing geological modeling or mapping, this is something which is maybe very familiar to you, because, think of a very, very simple setup that Elisa Heim constructed as an example, which I really like here. Let's say we have we are mapping somewhere. You see this surface up here. I hope maybe it's not big enough to see. The point is we have one rock type on the right side, one on the left side. This could be claystone, sandstone. And in the middle, we may have an area where we lack outcrop. If you transfer this idea to the subsurface, you can say you have, one borehole where you have one type of information, the next one next to it. The question is always, how do we fill basically the information that is missing in between? And now one geologist could come along and go mapping there. A geologist very experienced in structural tectonic settings. And she would say, well, I'm very confident. I know this region. There's sandstone this side, claystone this side. In between, so the clay should be above it in this stratigraphic setting. So I assume there's a normal fault in between. Second geologist could come along and say, yes, I agree, but maybe I found a measurement somewhere up there at the surface. And I would also say this is a fault contact in between somewhere, but the dip is maybe not 80 degrees, but 60 degrees. And now think of maybe another geologist coming along, and she's an expert in sedimentology, working in this field for a long time, and telling us, well, actually, I walk around and I see some indications here for a coarsening upward sequence. So there is not at all a fault contact. This is actually a different type of geological setting. And why is this relevant? Because all of this, what we see here, are aspects of uncertainty. And in some sense, we could say that if only we had, 1,000,000 or 1,000 boreholes in this block here every meter, we would be able to resolve this uncertainty almost to zero. But there's a difference in this type of uncertainty that we have. And this is that in general, we can say all of these aspects of missing knowledge are aspects of epistemic uncertainty. So epistemic meaning, this basically our state of knowledge is limited. But if you look at these upper two up here, these two are actually somehow similar. And the point is, in this case, we could say that we describe this uncertainty up here about the dip of this one feature of the fault as actually an uncertainty that we can describe by an approximate maybe mean value and maybe an uncertainty about this mean value of our dip. So we take this lack of knowledge in a sense and we transfer this into something that we can call an aleatory uncertainty, meaning that basically we can somehow replicate this uncertainty here by assigning a statistical distribution to this parameter. A quick context here in a sense, this is something aleatory referring to a die. So the big point being here that we have a lot of uncertainties in our geological interpretations and modeling and so on, but some of those we can combine and describe by distributions. Okay, let me move forward. Now, let's see which types of these which aspects of this typical modeling workflow can be described in this way. If we look at the conceptual, the framework to start from input information to a geological model, at some stage at the beginning, let's say we have here, a couple of boreholes and we have some information at depth. The first question we have to ask ourselves is, what is the complexity of the geology that we have here? And I'm showing here 3 examples. The simplest case would be to say that we have this red line, that we simply combine all of these interfaces by a single continuous layer. The second aspect, second type of model could be to say that we have a fault in between, and we assume there was an offset, normal faulting maybe in here. Or we may even go to a very complex model shown here by this green line, which would be like a folding pattern. Of course, very different tectonic interpretations behind it. But in this, if you only look at the data, this is basically what could be possible here. Based on this, if we now decide on one model, the next step is to then define the structure of a mathematical model that we can use now to perform this interpolation. And this means in this case, we could say we need to define now, let's say we have a continuous layer in here and faults. So we need to define how many faults do we have and how many interfaces do we consider. In the next step, then, we actually set the parameters of the interpolation function. So in this case here, we see, in one function combining these boreholes, but in between there is some uncertainty because we don't really know which mathematical interpolation function fits best to our geological setting, in a sense. And finally, we have the aspect of uncertainty in this position of our interface itself. As I said here, in this case of a borehole, you can argue that you may know this quite precisely there. But think of, picking maybe the interface position from a wireline log, and then again, the uncertainty can be quite high. If we look at these two aspects of uncertainty I mentioned before, then we could say that if we look at these aspects of conceptual modeling up here and the structure of the mathematical model, these are typical settings where we would create multiple scenarios, maybe, or we have to decide on one of these scenarios. But they are quite different and very difficult to combine into a single parameter distribution, let's say, so as an aleatory uncertainty. These aspects down here, these are aspects that we can usually capture in the form of distributions. Think of the interpolation function down here. We can say we use a geostatistical interpolation. We can basically set the parameters of our covariance functions or variograms as distributions. And in this case over here, this is very similar to the case I showed before, where we set the position of our point as being uncertain in a Silent distribution. And the point is, of course, that we are limiting ourselves. We are limiting ourselves to specific aspects of this modeling workflow. And the big question then is, if we do that, we make these decisions, we only look at some aspects of this uncertainty workflow. So do we actually still capture the full range of uncertainties in space? And now in the dialogue, say, maybe not necessarily, but let's look at this in a bit more detail. So in the intermediate summary, before we continue, we have seen that technically geological models, structural models, trend models, or these framework models, they can contain significant uncertainties. As we've seen, for example, in this study of Claire Bond, and there are in the meantime also several other studies investigating these aspects. Stochastic modeling methods now enable us to generate multiple realizations of these structural models if we can capture the distributions. And in this case now, I left, this is a different type of talk or different aspect of another webinar, or maybe, looking at some of the publications in this field. There's been now some work that also we have done in this field a bit to compare at least for these models where we do modeling in the field, that even if we limit our knowledge of uncertainties to quite a low part, basically to only these aspects where we can assign distributions, we do in fact see that these multiple realizations that we do with an automatic method, that they replicate, at least to a certain degree, the range of uncertainty that we would expect from multiple experts performing these interpolations. But this is still a lot of work to be done. Then I didn't talk about the visualization of uncertainty. Just adding this here, we can use methods like entropy, for example, as one way to very efficiently, to quantify and to visualize uncertainties in space. So up to now, that's all fine. But the big question still, to me, always was when we're looking at these results in here, okay, we do get some nice models that replicate somehow the stochastic nature of uncertainties. But the realizations in reality, those interpretations are created by geologists and the stochastic methods by algorithms, and they're of course lacking geological knowledge. So one of the aspects that is missing up to now are algorithms that actually maybe are able to learn more information about geology and so on, about the fit of a geological model based on data. And this is bringing us to the third part here now, the aspect of probabilistic geomodeling. And I'm getting almost close to my 36 minutes, so I have to quickly talk about the resolution. So the final part basically of our Greek drama. We see this problem set up. What are the methods that may help us to resolve this issue? And I would say I cannot offer you a full resolution, unfortunately, but at least some steps towards resolution maybe. Let's quickly see what can go wrong when we do these stochastic modeling methods. This is a very simple schematic figure, just showing you, one interface here and a fault, and these points describe our means, and the bars the variance of a distribution. And now what we do when we sample these realizations, we expect something which may look like that. So, similar to this model above, a normal fault, maybe slightly different dip and different angle, but somehow looks like what we would expect to get in the range of uncertainties. But what can also happen is that due to our configuration of points in our sampling, we suddenly get a configuration which completely messes up our interpolational algorithm, and we get quickly some blobs in space or some very weird geological representations. Or we can get something that may look reasonable in a geological context, but we see now here that the fault dip has changed from a normal fault in a sense now to reverse fault. And this would, of course, carry a completely different tectonic interpretation. So the point here is, of course, why does this happen? Well, our sampling here does clearly not respect parameter correlation, right? So we are sampling, in this case, independently. And this means that we may have correlations in reality that we simply do not consider. And why is this the case? Well, our automatic workflow is missing any type of geological knowledge in this stage. I mean, there's certain parts that we can implement in the interpolation approach, but there is no validity check in the end about our geological model. And well, the question is, what can we do about that? How can we actually train our systems, in a sense, to become more intelligent, in a sense, in creating these models? This is now where basically the thought comes into play to say, okay, let's look at probabilistic modeling, but let's look at models not only in this forward way of uncertainties, but actually as an inference problem. And the idea here being, okay, let's say we generate models automatically, but then we have a way to check which of these models are actually geologically or maybe geophysically impossible. If we do this, basically what we do is we describe again our parameters as random variables. Our aim is to estimate meaningful parameter distributions and correlations after checking new data, in a sense. And we'd like to quantify uncertainties in the predicted models. And if we put all of this together, then quickly this gentleman over here pops up in our head, Thomas Bayes, the reverend in the 18th century, who is famous now for basically being the first one to describe what we now call Bayesian statistics. And basically the point is that we should consider geological modeling not simply as a forward problem, but actually as a probabilistic inference problem. And I'm skipping here a little bit, just an example what this could mean. Let's say we have now here our spaghetti plot, but I'm showing this in 1D. So we have two interfaces here drawn in this blue and these green interfaces in here. And what I'm showing here is the distribution for these interfaces where we would expect them at depth. So this is depth down here. And we have here a very simple 1D model in a sense where we simply draw realizations from these distributions and we plot all of those models that we obtain in a sense here together, and we get these spaghetti plots again. Let's now say we have additional information. And this could be maybe from the fact that we know from the vicinity, observations in the vicinity that we always have between blue and green, we always observe a certain thickness maybe of this layer, and this thickness may still be uncertain because it's not precisely always 180 meters, but it's maybe 180 meters plus minus 20 meters or something. and a distribution here. So what we do now is we draw samples from this model. We compare this in a sense to the expected distribution of thicknesses. And then we find a clever way to only keep models basically with overall follow this distribution when we take multiple realizations. And in the Bayesian context, of course, you know what I'm talking about here. We have some prior information or prior distributions of parameters. We add information in the form of a likelihood function. We draw from the posterior distribution using a combination of those two in a sense, and we obtain an updated state of knowledge in a sense about the geological parameters in space. And if we combine all of this, we can draw this also as a nice node diagram. So we say, you know, up here, this beta, this is our prior information. We combine this with our posterior, with data in a sense, with these y's, and we update the state of our distributions beta by considering this additional information y. What does it also mean? It means that we are learning something about these distributions of our parameters. And that's just an aspect I would like to mention very briefly, but this is in some sense, it's an aspect of learning. Right? We are updating our state of knowledge and we are training a system with new knowledge. So nice, but the big question that I would like to talk about in the last minutes, Hadi, Sebastian, and we'll look at the watch, at the time here. So how do we define now meaningful likelihood functions? That's something which is then now getting more into the real question of applications. Well, hold my beer. Let's have a look. In addition to using these forward models only, we could say that we generate models, and in these geological models, we combine them with a geophysical forward simulation, and we then compare the obtained geophysical signal from this. That would be basically the right one if our model was correct and our geophysical model was correct and so on. We compare this to the actual measured data sets, and we actually then obtain an update of our geological model after seeing this additional geophysical information. That's something which has been now published in a couple of papers. Here's one example from a mine site. In a similar context, we can think of examples in geothermal. But now to conclude in our question, what we want to know is, of course, how can we use this information in our geothermal workflow from geology over mesh generation to process simulation? And the big point here is that, well, this is a bit more tricky because there are some elephants in the room here. And the first one is this aspect of mesh generation. And as I'm sure some of you know, whoever created meshes for simulations out of realistic geological models, this is a step that requires often a lot of tedious manual work. And we have these process simulations, which can take hours or days to simulate just for one parameter set. So in order to make this feasible, we first need to automate all of these steps. And we need to have process simulations that are fast enough that we can use these inference methods. Very briefly, looking at the mesh generation, there has been some work in this field to optimize this mesh generation approach. I would say, this is now in the challenges part really here. This is something which there's still a lot of work required in science, on practical applications as well, to get to methods that allow us to automate this meshing process. So if you're working in this field, I think this is a fantastic task, but also quite challenging to do this for reasonably complex models. The next step is process simulation. And here there's also been a lot of work. Let me skip directly to geothermal process simulations, where we can use now methods based on physics-based machine learning is one approach, which allows us to simplify or to substitute to find surrogate models, which allow us to generate realistic geothermal simulations for a specific parameter range, to be honest. So there's always trade-off. But what we do is we replicate this fully complex, basically, flow simulation model, for example, with a combination of extracted basis functions and neural networks. And we get to surrogate models that are then very fast to execute. And we have a couple of examples of these approaches in publications, which allow us then to take these simulations in full aspects like sensitivity analysis or uncertainty quantification, which requires a lot of forward simulations. Okay, this brings me a bit now to the end. Skipping over one part, which is, if we look at this entire workflow, an aspect that is also really challenging. Okay, let's include this at least a bit here. These are all these arrows in between, our connections between our prior parameters and our likelihood functions, basically our data, because all of this is nice, but it requires a lot of computational power and many forward simulations. And in the meantime, there's also been a lot of fantastic work on finding ways to speed up this inference process using methods from the field of machine learning mostly. So there's now Hamiltonian Monte Carlo as one type of implementation, and other very efficient sampling schemes, which make this workflow now, which at least takes it into the range of making it possible to combine all this information. So to sum up, this is our motivation in the end was to find ways to reduce this aspect basically up here of risk. And I could only show you a couple of small parts of attempts to get closer to an estimate of uncertainty and the associated risk in a geothermal project, for example. I hope I could show you that where there are ways forward to combine more and more information. I focused on the geology, but also in the field of process simulation and geostatistics. There's been a lot of work. And well, I say in the next couple of years, I'm looking forward to some really exciting more steps in this direction. One part that is also interesting, I think, and why this becomes now more and more possible, you know, in the end, the question is all of this accessible? Can we actually use it? And yes, in the meantime, there's so much exciting work in the field of open source projects. And now I place these questions in a really stupid place because I'm hiding GemPy, GemGIS, exactly those packages I've been talking about. But the point is, of course, that we now have a fantastic, ecosystem of open source packages, usually based on Python, but then in very efficient implementations using machine learning frameworks like TensorFlow, PyTorch, Theano. And on top of this, we have this layer of many new geosciences applications, geoscience-focused packages from all different fields of applications, which we can combine and create these really efficient and fantastic workflows. So now really the final summary, conclusion, and in our Greek drama, the end of our drama today. Probabilistic geomodeling and geothermal simulations. Basically, the motivation is to go from considering geological models and process simulations as a single best fit, which it never is, to considering all of these aspects as a scientific tool in a sense, which by essence we should treat as uncertain. The point is, of course, we can generate realizations, but we never know if we actually capture all uncertainty, if you like. So a nice quotation here from colleagues Nearing and Gupta: a range of plausible model is not a plausible range of models. There's always this aspect of the unknown unknowns. An interpretation of uncertainty is always that. It's just an interpretation. It's a model. In reality, uncertainty does not exist, at least not above the quantum level. But we replicate this somehow with models, and they also have limitations. My main point here is, a lot of our work is focused on ways to combine geological modeling and geophysical information. And the link to geothermal simulations, it's challenging. I showed you some very small glimpses in the interest of time here only, but there's been a lot of progress, and I think this is becoming now more and more in the range of the possible. Very next, I think these are exciting times. I hope I could stimulate a bit of thoughts and hopefully also discussions. There's a lot to do, and I think especially now with this, there's a huge interest now in geothermal topics. There is really a need to develop things in this direction, but there's also the possibility, because we have all these exciting developments from the field of machine learning entering into our field, and there's a lot of scope for combination of these methods to learn more about the subsurface and these geothermal simulations and projects. That's it. Thanks for listening. Sorry for being a bit over time.
Thank you very much. That
well,
was really nice and timely. Thanks a lot. We have plenty of questions also, and since we don't have a lot of time left, so I rather just pass it on to Sebastian to go through the questions that audience have asked you.
Okay. Yeah, thank you very much, Florian, for a really nice talk. And as Hadi said, plenty of questions. So I'm starting with one that came halfway through the talk, because you mentioned machine learning at the end.
Yep.
So Menji Zhao asks, thank you for the interesting presentation. Can your workflow be connected with machine learning to match geological images in our interpretations in a better way?
Yes, that's a super nice question. So if I understand correctly, what you mean is that we could maybe take, let's say, cross sections from our geological model and compare this to actual images from reality. We had a look at this a little bit. The question is, of course, as always, when we use machine learning, especially on visual comparisons, on image analysis, we need a lot of training data. One possibility would be to say we generate multiple models based on different modeling approaches. So what we could use is we could generate potential reasonable cross sections using kinematic modeling, kinematic forward modeling, like with methods like NODI, where millions of models have already been generated that represent a certain set of tectonic setting, let's say. So what we could do is we could train images that look like images or cross sections from a normal from a setting, an extensional setting with normal faults, and we could check if our model fits to this expectation. That's something we've been looking at a little bit. There's really a lot of small details, tricky details, well, small, maybe major details to check. What we have done, though, is to substitute this knowledge with topology. So one aspect is that we have been using topological aspects like connectivity, trained, let's say, for example, on a cross section. So geologists could tell us, I would expect this to be a realistic image where we have certain connections across a fault, let's say, and we can take our models and check if these connections are also represented in the model. And this is a way to integrate this knowledge, in a sense, from geology in a more soft way, because we don't really look at the exact fit, let's say, of interfaces. I hope this answers a bit the question.
Yeah, and thank you. And there's a follow-up question from Hermonio. It's a two-part question. He says, stable diffusion IAML models are showing a tremendous success in generating these realistic images. I was wondering if that technology could also be used for generating realistic, consistent geological models as well. Commented already on the machine learning, but perhaps a comment in general on the stable diffusion models.
So we did not look at stable diffusion yet, and I don't have this in my backup slides, but there's some really exciting work by Mike Hillier from Canada, who has been working on using graph neural networks and convolutional neural networks to generate these implicit geological models. So not the image, the full image in a sense, but these scalar fields that are underlying these implicit representations. And this is super exciting because one of the challenges that we are facing in these methods is especially that we use things like RBF or geostatistical approaches, where we need to invert basically a matrix. And this is super expensive. We can substitute this with these convolutional neural networks by basically simply optimizing our network weights. And this can be applied to, I think we have now, Mike tried it on 10,000s or hundreds of thousands of data points. This is super exciting. So if you look for Mike Hillier, and I'm also co-author on the last paper there, this is some really interesting work in this direction. Stable diffusion, something which we did not look at yet. It's true. It's also a good idea.
Mm-hmm. Thank you. Take a question here from Willemijn, and again, it's two-part questions. He says, thank you very much for the interesting presentation. Can your workflow be used for predicting used seismicity in the sense that we define faults, and orientation, friction coefficients? Can we learn about pressure depletion or increase with impact on the stress state quickly?
Okay, so maybe the point would be to say, but with these probabilistic methods, always the question is if you can define a model that, in a sense, generates the data. So what we need, if we look at induced seismicity, we need to have a model that connects the fault locations and so on with the expected seismicity. So let's say a combination with mechanical models. That's something we've been looking at a bit with colleagues here in Aachen. And then we could say we have some, let's say a prior assumption about the position of a fault. And then we take measurements of the induced seismicity and we update the expected position of a fault based on this additional information. And this then, of course, may give us a better estimate of where to expect the further induced seismicity, because we get a better picture about the structures. Maybe this answers a bit the question. So we can certainly use it to combine different aspects of knowledge, and we can then use our updated knowledge to update our predictions and hopefully be more precise.
Okay, thank you. You made the case for reduced order models, neural networks, etc., to response surface to accelerate some of the simulations, integrate them better with the geological modeling. So Korean Tigers, whoever that is, says many thanks for the talk. Do you use neural networks for reduced order modeling? Do you use autoencoder? What's the cost of the training?
Excellent question, and someone who seems like has already a bit of experience in these approaches, maybe. What we do here is we use what is called the reduced basis method. And Sebastian, you're right, you could also use different types of response surfaces. There's been a lot happening in the field of reservoir engineering, hydrogeology. We've been using these so-called reduced basis methods now for some years, and what we like about them is that they allow us really to keep the physics basically in our surrogate model. How does it work? Very simply spoken, think of a signal that we would like to replicate with a Fourier series. We need to first find the main components basically of the series that we need to consider. And then we can basically, the more of those we take, the better our estimate of the signal gets. And we do a somehow similar approach, but using these now states, let's say the state of pressure or temperature here. What we try to find are basically the most, the functions basically, or modes, which represent in combination the state of our physical system. And this is done by POD, proper orthogonal decomposition, but on a state basically of the physical equation. So we know that basically all the combinations we generate, they are also reasonable in the range of the physics that we implement. And then we need to combine those realizations in order to get our actual representation of physics. And this combination of weights, so we assign weights, similar again to a Fourier series, and the training of these weights is done using neural networks. And this has been an approach that has come up in the last 2 or 3 years only in mathematics. But it's super efficient, and it allows us to get to reasonably good approximations in a fair amount of time, let's say. What do we need? How many forward simulations? Yes, it's true. There's a training phase where we need to train basically this network, of course, and we need to determine these physical states. But this pays off fairly quickly. So if you look at the papers of Denise, it's down here. So Denise Degen, Ryan Santoso, one of our PhD students working on this topic, they have some very nice comparisons for different types of settings, where we look at the cost of training phase and how many realizations you need to pay off basically this training phase.
Okay, thank you. And Alex Analidis has a follow-up questions. Is there any validation carried out on the reduced order models with reference models?
Yes, exactly. Yeah. So what we do, of course, so if you train these models, you compare this to the what is called terminology. Oh, it's been a long day. With the full finite element simulations, for example. So let's say we have a finite element simulation. So we have the full finite element simulation, and then we compare the generated models to this full realization. And the nice thing is, if we stay with elliptic or parabolic PDEs, elliptic especially, parabolic as well, then we even have a guarantee on the error of the approximation. That's, I think, shows you the power of this approach. It gets tricky when we go to nonlinear settings and especially hyperbolic problems. But for elliptic and parabolic, you even have a guarantee on the error that you make with your reduced model. If you look a bit at these papers of Denise, and there are some nice references and overview papers in there as well, this will certainly show that.
Then if you go to nonlinear problems, you can also think about how do you enrich then your training data in the areas where the errors are largest to reduce the model errors. So
that's a bit the case that is done. So when you select on the number of realizations that you need, This is a greedy algorithm where we say that we generate more realizations until we get our error down to a certain level that is acceptable to us.
There's still plenty of questions. I'm going to take one final one by Tears. It says, what probability distributions? Teachers. Sorry.
This is our teachers.
Oh, okay, sorry. Apologies for that. What probability distributions are used to create the different models? Gaussian, uniform, Poisson. What is the motive behind your choice?
Fantastic. Do I have this example now here? In the interest of time, let me quickly answer. See the wrong backup slides here. There are definitely many of these are choices, right? So this is, as I said before, the model of uncertainty is also a model, and it's valid in the range of our choices. One of those important ones is the choice of distribution. Now, if you're a bit familiar with Bayesian inference, we know that it's completely fine to make subjective choice about the distribution we use. It can be based on our best knowledge. It can come out of expert elicitation, let's say, so sitting together with multiple experts discussing which distribution is reasonable and what parameters do we give this distribution. In some cases, we can actually decide on a distribution from measurements. Now, think of the case that we may have this lack of outcrop that I showed before. We may have information here, information there. In between, we don't know where our interface is. Then we could say we take a uniform distribution between those endpoints. It has to be somewhere in there, but we don't want to give any best guess about it. But let's say that you have additional indications like geomorphology or additional information. Then you could say I'm using maybe a normal distribution just to say that I'm a bit more certain in one region. But think also about things like measurements in the field. So we could use things like orientation measurements in an outcrop. And that's actually something we have done. So we can now, instead of just taking one measurement, you take, let's say, 100, which is now easily possible with, automatic compass methods and iPhones, mobile phones, and so on. And then we actually determine the distribution of orientations based on the measurements. So it's always a lot of aspects that come into play here. The aim is, of course, that if we combine it with additional information on top of it, in this Bayesian inference context, then the prior distribution, of course, always plays a role, but it should not be the full dominating choice, let's say.
Okay, as I said, there's still questions, but we are reaching the full hour. So, Florian, thank you very much for a really nice talk. And some of the audience actually comment on the great setup that you have and ask if that you're using chroma key here in the background. So thank you for an excellent talk. Thank you for taking the time to answer all the questions, and to our audience for asking all these insightful questions. And with that, Hardy, over to you for announcing.
Yes, thanks a lot. So I'll be quick. We will have the next month webinar by Professor George Hirosaki from Rice University. George is a well-known figure in the geochemistry and chemical processes in the subsurface reservoir modeling and simulation. So from geology and understanding how the reservoir looks like, we move on next week to see how can we model now the processes inside. And ultimately, the need will be that we all work together in one framework, that everything is coupled. And so, Florian, you have an open invitation to come over to Delft. So we discuss a bit more and in more kinds of pen and paper based, and get to do some work together on this fantastic topic that you just delivered. Thanks a lot, everyone. Enjoy your evening. It's a bit gray and wet here, but wish you all the best.
Thank you very much, everyone. Bye-bye.
Everyone. Bye-bye.
Thanks for being here.
Listening.